In this lecture, we continue our discussion of matrix concentration inequalities. So the plan is first to do a quick recap of the last lecture that we had, and the main tools that we used to build up these concentration inequalities. So this is all going to be a quick review from last time. So the first step was to define an exact analogy to the scalar setting, matrix moment generating functions and cumulant generating functions. The matrix MGF and CGF, and these are defined in precisely the analogous manner. So for X, a random Hermitian matrix, and theta, any scalar, any real scalar, we define mx of theta as the expected value of e to the theta x, and xc, x of theta, is defined as the logarithm of this. So recall also from last time that we had defined the matrix exponential. So for A, again, a Hermitian matrix, we had defined e to the a through the power series. I plus a squared plus a squared over 2 factorial, and so on. And recall that we had shown various properties, in particular properties relating to the eigenvalues and eigenvectors of a versus e to the a. So recall that if v is an eigenvector with eigenvalue lambda, then this implies that v is also an eigenvector of the matrix e to the a with eigenvalue e to the lambda. So you may just want to refresh your memory and just show this. It's quite a simple exercise, and it comes directly from the definition above. So we use this in our first result. For y, a random Hermitian matrix, and t any scalar, we can get bounds on the probability that the largest eigenvalue of y exceeds some scalar t. This is less than or equal to the infimum over all positive thetas, e to the minus theta t times the expected value of trace e to the theta y. And the probability that the smallest eigenvalue of lambda is less than some t is again less than or equal to the infimum over this time negative thetas, and then the rest has the same form, e to the minus theta t, that's correct there, that minus sign, expected value of trace e to the theta y. So recall, so here we had a departure from the general development for scalars, and the reason is as follows. So our typical use case is when we have y equal to some sum of random matrices. So the simplest setting is when we have the sum of IID random matrices. Again, exactly in analogy to the scalar setting, since this is what we want to prove concentration for. Now, in the scalar setting, the exponent we have the exponent here and here, and you'd have a sum in the exponent, which would become a product. But for matrices, this is no longer true. So the key difficulty arises from the following fact. If a and b do not commute, in other words, if ab does not equal ba, then it may not be true that e to the a plus b is equal to e to the a times e to the b. So this is true if a and b commute, but it may not be true if a and b do not commute. And this is this requires some additional tools. So again, for scalars, if we have something like y is equal to the sum of xk, then for scalar random variables, the moment generating function of y, which is m of sum of xk, this is equal to the product of the generating functions of the individual xk's. And as we'll see, as we've already seen from some examples, typically quantities involving y are difficult to understand. Quantities involving only xk are easier. So this does not hold in general for matrices, unless we're in the extremely special setting where all the xk's commute, and that's typically unlikely. So the way around this, as we discussed last time, was to use this the only piece of heavy machinery in all of our discussions here, which is a theorem by Lieb. And this theorem says the following, that if H is a d by d Hermitian matrix, then the function that maps a matrix A to the trace of x of h plus log a, so note h is fixed, it's a that's the variable here, is concave on the positive definite cone. So note again that if a is a scalar, then this is just a linear function of a. So it's linear. It's not even concave. So concavity really is a property that that emerges only for matrices. So how do we use this? We use this with the following corollary that says that if the expected value of trace of exp of sum of theta xk, okay, so this, you should recognize this as exp of theta y, is less than or equal to the trace exp of sum of k log of the expected value of e to the theta xk. So what we've basically done is we've taken something that has the sum of the xk's in the exponent to something that has only m of xk of theta. So this is basically this corollary, which is a consequence, a simple consequence. We proved it last time, basically just using iterative expectation and Lieb's theorem. Is what replaces the expression that we have and we use for scalars. So we essentially have something that relates with inequality, a combination of the moment generating functions of the individual xk's rather than the product expression that we have above. So this allowed us to give what we called the master bounds. So putting these together, we got the following master bounds for sums of independent, not necessarily identically distributed, random matrices. So let's suppose that xk is a finite sequence of independent, random Hermitian matrices. then, and again, this is exactly what we gave last time, just quickly summarizing it, then the expected value of the largest eigenvalue of the sum is less than or equal to the infimum over all theta of 1 over theta log trace exp sum over k of log expected value of e to the theta xk. And similarly, we get our lower bounds, lambda min of the sum of xk's is greater than or equal to the supremum over negative theta, 1 over theta log trace exp sum over k of log e to the theta xk. And we also have analogous bounds to the probability of the tails. But since I wrote this down last time, I won't repeat it right now. But where does this come from? The proof of this is straightforward. We simply combine the previous corollary with the first proposition that we gave. And that's it. The main question remains how to use this. So this doesn't give us any bounds. We still have some work to do. So the typical recipe, and we saw a few examples of this last time, and we'll see some more this time, is 1, express whatever you want a concentration of, express as a sum of random matrices. I should say of independent random matrices. Compute, and let me call these xk, then compute the moment generating function, and then plug into these master bounds.